Just think about this for a second. Imagine taking a tiny little piece of metal, something you could hold on your fingertip, and zooming in. And I don't mean just a little bit. I mean zooming in millions of times, pushing past every barrier until you can actually see the individual building blocks of our entire world. For the longest time, this wasn't just hard, it was considered impossible. But today, we're going to talk about the incredible story of how a few scientific rebels made that impossible dream a reality.
All right, let's start this crazy journey. We begin by magnifying the surface 1,000 times. We're already way past what you could see with a normal magnifying glass.
Now, let's crank it up to 100,000 times. Suddenly, the world you and I know is just gone. It's been replaced by this strange, almost alien landscape. But we're not even close to where we need to be.
And here we are. At 50 million times magnification, we finally see them. Every single one of those little blobs you see, that's an individual atom, a sight that for most of the 20th century, physicists thought we would never see. So the big question is, how on earth did we pull this off? Well, it turns out it's not as simple as just building a better magnifying glass. There are some serious fundamental laws of physics that get in the way. Let's break down what those are. So the first and biggest hurdle is something called the wavelength problem. The rule is actually pretty simple. You can't use light to see something that's smaller than the wavelength of the light itself. And here's the kicker. Visible light has a wavelength that's thousands of times bigger than a single atom. That's literally like trying to figure out the shape of a single tiny grain of sand by poking it with a giant beach ball. It's just not going to work. The light waves just bend or diffract right around the atom, which makes it totally invisible to any optical microscope, no matter how powerful. So if light's the problem, what do? Well, the answer wasn't to find a better kind of light. It was to get rid of light altogether. And the key, first figured out by a physicist named Louis de Broglie way back in 1924, was to use electrons instead. You see, de Broglie had this revolutionary idea that all matter, not just light, acts like a wave. And here's the genius part. An electron's wavelength depends on how fast it's moving. So if you can accelerate an electron to, say, 80% of the speed of light, its wavelength becomes ridiculously small, over 100,000 times smaller than visible light. All of a sudden, you've got a probe that's actually small enough to see an atom. Okay, great. So you have these tiny electron waves. Now what? You've got a whole new problem to solve. You can't use a normal glass lens, like in a telescope, to focus a beam of electrons. You need a completely new kind of lens. And this problem was cracked back in 1931 when Ernst Ruska and Max Knoll built the very first Transmission Electron Microscope, or TEM. And it was just a brilliant piece of engineering. Instead of glass, they used a coil of wire to create this powerful, donut-shaped magnetic field. And that field acted like a lens, focusing the electrons as they shot down this vacuum tube. The beam would then pass through a super thin sample, creating a kind of shadow on the other side, which was then magnified onto a screen. And you know what? It worked. It worked amazingly well. By the mid-1930s, the TEM was getting magnifications that blew every light microscope out of the water. It opened up this whole new hidden world. We could see bacteria and viruses for the first time, which totally changed medicine. It really felt like seeing atoms was just right around the corner. But then science slammed into a wall, a really big one. This wall had a name, the aberration limit. In 1936, a physicist named Otto Scherzer published this bombshell paper. He had found a flaw in the magnetic lens that he claimed wasn't just an engineering problem. He said it was mathematically, physically unavoidable. I mean, his mouth was solid. It basically said, that's it, folks. We're done. The electron microscope had hit a brick wall. And this wasn't just about getting clearer pictures, right? This was about everything. Designing new medicines, creating stronger materials, building faster electronics. Progress was about to grind to a halt. So what is this so-called spherical aberration? Well, on the left, you see the dream, right? In a perfect world, the lens focuses all the electrons down to one single razor-sharp point. But in reality, the magnetic field in these lenses is a little stronger at the edges than it is in the middle, so it overbends the electrons on the outside of the beam, making them focus too early. And what's the result? A blurry, smeared-out mess. Now, with the regular camera, this is a pretty easy fix. You just add a second lens that's shaped the opposite way, a diverging lens, and it cancels out the error. Simple. But, and this is the killer, Scherzer proved that because of the basic laws of magnetism, you just can't make a simple magnetic lens that diverges electrons. Every single one will always converge.
The fix was for all intents and purposes impossible.
And that's what kicked off this incredible 60-year-long scientific quest. How do you solve a problem that physics itself says is unsolvable? Well, the answer, as it turned out, wasn't to build a better lens, it was to break it.
Just look at this timeline. It really shows you how long this problem just sat there, for over 60 years. Sure, scientists found clever little workarounds, like in 1970 when Albert Crew managed to image single heavy atoms. But that fundamental blur was always there, this hard limit on what we could truly see, until a team of so-called mavericks showed up and decided to try something completely different.
So, let's meet the heroes of our story: Knut Urban, Max Heider, and Harold Rose. In the scientific community, these guys were known as troublemakers. Why? Because they were chasing an idea that sounded completely nuts. Their plan was to do the unthinkable, to intentionally break the image in a very specific, controlled way in order to fix it. Okay, so what was their crazy idea? It was this beautiful, counterintuitive gambit. Instead of a simple round magnetic lens, they used these weird six-poled magnets called hexapoles. The first set of magnets would actually distort the electron beam on purpose. This created a new, tiny flaw, but one that had the exact opposite effect of the original blur. Then, a second set of magnets would bend the beam back into its original round shape, and the result? A perfectly focused beam, because the two arrows had perfectly canceled each other out. So fast forward to July 1997. The money is almost gone. This is their last shot. They install their brand new corrective lens system into the microscope, they hold their breath, and they fire it up. And nothing. It didn't work. The image was all wobbly and unstable. You can just imagine the feeling in that room. It looked like 60 years of frustration was just gonna keep on going. But here's where the story takes a turn. They didn't just pack up and go home. They decided to just let the machine rest for a while, to let all those complex magnets settle into place. And in that quiet moment, absolutely everything was about to change. So this is what scientists had to work with for more than half a century. It's the view from behind Scherzer's brick wall. You can kind of tell that there are structures in there, but they're all blurry and indistinct. You can't really see the individual atoms or accurately measure the spaces between them. It's like looking through foggy glasses. And then, at 2 o'clock in the morning, the team went back and turned the machine one more time. And this is what they saw. For the very first time in human history, a perfectly sharp, aberration-corrected image of atoms. The blur was just gone. As they described it later, it was pure magic. The wall was gone. They had broken through. You have to understand, this wasn't just a slightly better picture. This changed everything. It was a total game changer. For the first time, scientists could see the actual, real atomic arrangement of materials. They could measure the exact distances between atoms. They could even identify different kinds of atoms within a structure. It kicked off a massive revolution in almost every field of science you can think of. You know, the story of how we finally saw the atom is just this incredible tale of persistence, of refusing to give up even when all the experts say something is impossible. And it leaves us with this one huge, exciting question for the future. Okay, now that we can finally see the fundamental building blocks of our world with perfect clarity, what are we going to build with them?